So we're going to talk about unsteady flow. Before we were talking about steady flow. And could someone tell me what I meant by steady flow when it comes to groundwater and well pumping and the like?
Discharge doesn't vary with time.
Okay, so discharge does not vary with time. And that means also that we've given it enough time to equilibrate. And so if we've got, here's the ground, here's a well, got groundwater table in there, got a cone of depression, and that well's been pumping for, days and days and days at a certain steady discharge rate. The groundwater has had time to adjust and equilibrate, and so it's not changing. The elevation of this groundwater isn't changing over time. So that's steady flow. So unsteady flow is opposite of that. And so when we have a well and we start pumping, maybe the groundwater is level initially, it's going to start to go down over time. And we kind of develop this cone of depression. And I should say this is, we'll call it unsteady groundwater flow, because what we're doing here is we're going to be pumping at a steady rate, but the groundwater is going to be responding and changing over time. And so by unsteady flow, I don't mean that the pumping is changing over time. I mean that the groundwater is changing over time. So it's transient. It's kind of the big key here. So transient means it's changing with time. So we'll talk about unsteady flow just at a conceptual level. There is a lot of ways we can calculate, for example, hydraulic conductivity and transmissivity. Those are the two things we talked about in the last lecture, which are properties of the aquifer as well as the fluid. And so the reason why we do these unsteady flow tests is to estimate properties of the aquifer. There's other properties too, but these are the two I'm going to talk about. And the idea here is that really to get kind of steady state conditions, it's going to take days and days and days. And if you're a consultant, so like an environmental engineer, and you're getting paid, or a groundwater engineer, hydrologist, you're getting paid to go test the aquifer and figure out, how fast this contaminant plume is going to be moving from one place to the next, or if you want to try to find out how much yield this well could produce, you've got maybe a day to go out there and do this. And so that's why we do a lot of tests that are related to unsteady or transient conditions. And so the first test that I'm going to talk about is the pump test. And the pump test is as exactly what it sounds like. You start to pump water at a constant rate. And then you observe drawdown from a nearby well. And so what this data might look like is, so we've got a well right here. And you're pumping and pumping, and you're gonna, here's our steady state condition. And in this well, you've got a logger, which is usually just a kind of a pressure transducer that tells you the pressure ahead, and then you can transfer pressure to height using the hydrostatic equation. And so as you're pumping over time, we're going to be drawing the water down. And you can measure that drawdown over time. So the data is something like this, we might have drawdown say in meters, and then we'll just have time over here. And usually the drawdown, depending on the hydraulic conductivity, has some nonlinear shape. And so it drops quickly and then slows down over time. And so we can go back to the kind of the similar equations that we looked at previously to estimate things like hydraulic conductivity based on this curve and the slope of this curve. You kind of fit a line to it and put that line into a hydraulic equation. So for a pump test to work, we need relatively high hydraulic conductivities. What kind of aquifers have relatively high hydraulic conductivities? What kind of media are we talking about here?
Like very porous.
Porous. So what kind of substances, what kind of things in the
Like
ground are porous?
like sand,
Sands.
cobble.
So alluvium, do you guys remember what alluvium is? It's the stuff brought down from rivers, sand, cobble, gravel. Alluvial aquifers next to the river made of river sediment are often very high conductivity values. Maybe limestone, I'm not quite sure, it's a porous kind of bedrock, could be high conductivity values. Okay, so that's a pump test. And what I'm going to do is I've made a handout that walks through pump test and slug test, and there's a lot of different methods. Um, Last semester, I went through these methods. I just thought it was too complicated, and we really don't have enough time at the end of the semester to get into how to do these things. So if it's something that interests you, I'm putting that information on the module, on week 14's module. And you can take a look at it or just download it and save it for later um, if that's anything that ever comes up. I also give you the readings in the textbook that's associated with these two kinds of tests. And that's just a note in general for this class. I put a lot of resources on the modules. Some of them I ask you to read in homework assignments. Some of them I just have there for reference. I know given the amount of work you guys have, you probably rarely get to look at those. But if hydrology is of interest to you and you think you might be doing this kind of work down the road, I'd recommend at the end of the semester going through and downloading everything that I've put up there so that you can save it and kind of just have a hydrology folder and you've got topics and documents. I've put reports and different kind of technical resources there for you outside of the textbook. All right, so the next kind of test we're going to talk about is the slug test. And the way a slug test works is you just have one well. It's really hard for me to draw straight lines. And what we do is we put a slug in, and the slug could either be a positive or negative displacement. I usually think of it as a negative displacement, meaning you're taking water out instantaneously, or at least close to instantaneously. That's a hard one. So a slug could be a baler, and a baler is just something on a rope that is hollow and that will go down into the water. So it's usually like a plastic, PVC kind of thing with a weight on it, and it'll have I'm not exactly sure how they work, but it'll have a lid like this that's connected. And so I think you have like two ropes or something like that. Or maybe you just like put it down and then when you pull it up, that lid closes on it. And so it'll fill with water. And then when you pull it up, it's going to take that water away from it. So before you put the baler in, the water level is looking like this. And then this is not a different well, this is just kind of in the next time step here. Actually, let me just, I'm running out of room here. Okay, give myself a little, we're gonna zoom into this well. So you put that baler in, it goes in, and then here's our groundwater level at kind of like steady state. And then all of a sudden that baler comes out and we've dropped the water level a little bit. So our baler is full of water and it's coming out. And so you take this slug of water, you kind of remove it really quickly from the well. And then in that well, you have a data logger that monitors how this water level slowly adjusts and comes back up over time and renormalizes. And so it's going to be similar data as before, where you have time and then we'll just say level. And so you take the slug out and the level's low. And then over time it's gonna, or maybe it's gonna go, I can't remember exactly what it's gonna look like. I think it's like here. It's gonna be some sort of asymptotic thing, right? You're gonna end up back at your original level asymptotically. So the slug test works for aquifers with lower hydraulic conductivities. So if you do a well anywhere outside of the floodplain here, you've got that nice clay stuff. Either it's the Morrison Formation or something else. You're gonna have pretty low hydraulic conductivities, and so you might need to do a slug test. It might take hours for this to recover, right? And so that's one of a test you can do within the well. Again, that's going to be covered in the handout that I'm posting on the modules here.
What's the what's the purpose of these last two tests? Or like what are we trying to find?
The tests are specifically to find the K value. So you're trying to test properties of the aquifer. I'm not going over all the equations and stuff like that, and so it's a little bit out of context. I just wanted to like tell you guys these things exist. And the idea here is that you go back to the equations that we talked about in general, like the Dupuy equation, which relates groundwater flux and flow to hydraulic conductivity to the gradients of these water table lines. And you can basically back calculate a K value or some other property of the aquifer. So if I want to know what's the hydraulic conductivity of the aquifer, if I want to know how much water I can extract from this at steady state, to supply or irrigate or something like that, I can go out and do these tests to get characteristics of the aquifer that can then tell me the hydrologic properties of it and hydraulic properties of it. Let's quickly look at what a well actually looks like. I think this is it. Yep. So this would be the handout that I'm posting. Oh, here we go. So here's just a schematic of what a well looks like, kind of how you construct it. This is part of the handout that I'm posting. So you go in with a drill rig, right, and drill a big hole and put in a number of things. And different wells are going to be constructed differently depending on their purposes. Here's a typical design for unconsolidated formations. Unconsolidated means it's not bedrock. It's just soil. And the idea is you put in the well, and this is usually like a PVC kind of pipe. And it's going to have slots on the bottom or a screen. And the screen part is where the water enters. This screen could be really, really, really long. You could have hundreds of feet of screen, or you could have just, a little bit of screen on the bottom. Depends on how much flow you need to get out of this well. That pipe is put in the ground with the screen. It's got a cap on the bottom, a plug, right? Usually you want to put fill in around the screen, and that's going to be sand, because sand has a high hydraulic conductivity. And then there's a seal of bentonite. Bentonite is a clay material, you're probably familiar with it. That bentonite is poured down above the well screen. And so what that does is, you can imagine when you drill a hole in the ground, you're creating preferential flow path for surface water to go down. You don't want surface water coming in here, coming down your hole and contaminating your well. Surface water is disgusting, typically. At least it's going to have bacteria and chemicals and stuff in it. So that seal is gonna seal that well up pretty well. It can be several feet thick, and usually just kind of pouring a bag of clay down there and putting water in there. Then there is another seal. In this case, a bentonite grout is put in here, and this is like cement and bentonite for the maybe 4 to 5 feet up to the top. And that is your kind of more permanent seal around the well. Usually there's a concrete pad or riser or something like that, and then a cap or maybe the pump. If a pump is put into a well, there's a couple ways to do it. You can put a well in and just kind of create suction and lift it all the way up, or you can put a well in on a tube, and the well goes all the way to the bottom where the water is, or sorry, the pump, excuse me. The pump goes down here, and the power source goes down here, and then it pumps up a tube out into your, wherever you use it, into your supply line. All right, I wanted to take the rest of the time to go over some examples, some example calculations together. Do you guys have any other questions about wells and well testing?
How much water can you get out of a well, or does that just depend on how much water is in the ground? How much water there is?
I don't have some real numbers on the top of my head, but people put some really big pumps on some wells for agriculture or for municipal supplies, and they're pumping out thousands and thousands of gallons a day, depending on the situation. So if you get a really deep well and a really productive, high hydraulic conductivity aquifer, you could be pumping out, in a well field, typically like a water supply for a city might have a well field where they have multiple wells, across a large area. That can be the supply for a whole city. So, millions of gallons a day. Usually those are going to be distributed not in just one location, but, across an aquifer. In Florida, a lot of water supplies come from aquifers like that. All the way down to a household well, residential well, which might pump at 30 to 50 gallons per minute, something like that. Okay, so the first groundwater problem I wanted to do is the direction of groundwater flow. This is kind of a basic problem, and the idea is we've got a well field, or in this case, you need at least 3 wells to triangulate. So here's well 1, well 2, and well 3. And these wells are drilled into the grounds. We've got an unconfined aquifer, although that doesn't really matter. This would work for a confined aquifer. And you use a depth meter, and so you basically have a piece of tape with measurements on it, and then it usually has like a little electrode, and it's powered or battery powered, and you reel it down into the well, and then it'll beep at you when it hits the water. So you can tell the depth to the water from the well. Let me just draw that out, because this is kind of a good thing to know. So we lower a little tape down there, and it tells us how the depth to the water, right? So say that's D. Usually the way it works is you'll know the elevation at the top of the well casing. And then you're measuring that depth based on that elevation. And so because we want to deal with head is the energy in the water, which is, in this case, if it's unconfined, is going to be equal to the elevation. So we need to convert that depth to elevation. In which case, if say the elevation at the top of the well is 1,000 feet, then we just do 1,000 minus D to get our head at this water level. Does that make sense? So ultimately, we want to deal with units of, or we want to deal with the elevation of the water surface. All right, so we've drilled these wells in, we've measured the head, meaning the elevation. And so in this case, H1 is equal to 26.2 meters, or sorry, 26.26 meters. H3 is equal to 26.07 meters. And then H2 is equal to 26.2 meters. And then we could also measure the distance between all of these, right, to get a length. So given this scenario with these wells, we want to find the direction of groundwater flow. And then we can also, from there, calculate the hydraulic gradient for this well. So the way we do this is, first, I'm going to erase that little well example over here. The way we do this is we're going to find the intermediate well, meaning the well with the middle head value, in which case it's number 2. So we have 26.26, 0.20, 0.07. So this is our intermediate well over here. And then we need to find the location along the line connecting the opposite 2 wells. So I'm going to try to draw a straight line here. Oh, not too bad. We need to find the location on this line where this head occurs, where this elevation of water would occur, you know, and that's just going to be through linear interpolation. We're going to assume that it's linear, that's kind of a plane, that the water surface here is a plane. So that's going to be somewhere along this line between 26.26 and 0.07. So how do we find that distance? Anybody?
Well, you just need the distance between the 2 wells.
Well, yeah, so we do need to, we need that distance between the 2 wells. So 20, I'm going to give that to you, 215 meters. How do we find the distance between where this 26.2 would occur between these 2 points?
You just plug it into the linear interpolation equation.
There you go. All right, linear interpolation. And so we're just going to kind of do a little homemade linear interpolation. First, we're going to calculate the slope between the two wells. And so that is 26.26 minus 26.07 divided by the distance. And we'll just say S slope. In this case, if we calculate that, it's equal to 0.00088. So that's our slope. And then instead of, I never remember the linear interpolation equation, so we just kind of do it like a word problem. So if we say we want to find H2 along this line, so H2 is 26.26. So what we need to do is say H1 minus our slope, right, because it's sloping down this way, times some number, and this is the distance that we want to find, is going to be equal to H2, which is 26.02. So this is the equation we have to solve for linear interpolation. So let's go ahead and do this. 26.26 meters minus 0.00088 times x is equal to 26.20 meters. And then we can just solve. We end up with 68 meters. So 68 meters from our first well is where we are gonna hit 26.2. So I'm gonna draw a line to there. And what we've drawn here then is a contour line, right? Where we have equal groundwater elevation from here to here, assuming that the groundwater surface is a plane. So if I were to dig a well at this point and this point and this point, I should, more or less get this elevation of my groundwater in the well. All right, so we did some linear interpolation. And now to find the direction of groundwater flow, all we need to do is well, I'll let you guys tell me what direction is groundwater flowing if I have a contour. Is the water going to flow with the contour or against the contour?
Against.
Yeah, so it's going to be perpendicular. And in this case, this is high and this is low. So here's our direction of flow. Perpendicular to that contour. All right, good job. If we wanted to calculate the hydraulic gradients, we would simply find the slope between this contour and a given observation. So we know, or we could really just do it from any one of these wells as well. So actually, no, the slope is not quite it. Yeah. So hydraulic gradient in this case is really just going to be the slope of the groundwater between any two of these well points and the distance of it. All right, so that is groundwater flow. Let's look at a quick Darcy's law problem. So this is going to be based on two wells. So we've got a sloping ground. We've got two wells going down into an aquifer. We've got a water table that is also sloping. And we've got a distance between these two wells, 780 meters. We know that the altitude, or the elevation of this well is 100 meters, and of this well is 98 meters. And we measure the depth to water in both of these wells. And we find out that this one is 15 meters, and this depth is 18 meters. All right, so the question posed is going to be calculate the rate of groundwater flow per unit area. So we'll start with Darcy's equation, or Darcy's law. And I originally posed it to you as big Q, which is volume over time, right? Is equal to area times a hydraulic conductivity times dH over dL, which can be approximated as delta H over delta L. We want to estimate, well, we're actually gonna assume a value of K for this problem. We want to calculate Q, and we've got enough information here to calculate the gradient here. What we're doing is we're dividing by area, and we're getting lowercase q, which is discharge per unit area, which has units of length per time. So if we divide volume by area, we're just ended up with length. And so little q is going to give us length per time. That's the groundwater flow per unit area. So to calculate the hydraulic gradients, we're going to need the head. And from the last problem, I'll ask Val to tell me, how do I calculate the head at these two wells? Okay, how about Christian?
We try to do like the difference between the height to the water and the second one to the water.
Yeah, so we're just going to take that. So head as units in elevation, and we need to be able to compare. We can't compare 15 to 18 because these well casings have different. Sorry, I didn't write that correctly. This should be 15 and 18. These well casings have different elevations, so the depth is really arbitrary, or it's really relative to the particular well. So we need this difference here, and so each one, if this is well number 1 and this is well number 2, each one is going to be equal to 100 minus 15 equals 85 meters, and then H2 is equal to 98 minus 18 is equal to 80 meters. So these are our two H's, and then we can go delta H over delta L to get our hydraulic gradient is equal to 85 minus 80 divided by 780, all in meters, and that is going to be equal to 0.0064. So that's our gradient. To find the hydraulic conductivity, we calculated it we can calculate that if we know a flow rate, but we don't know the flow rate. And so we're going to have to assume a hydraulic conductivity. And we can, for example, when you dig a well, you come out with samples, right, at different depths. And so we can say, okay, this is a relatively homogeneous aquifer, and it has a loamy kind of soil. Based on the soil texture, maybe you take it back and do more of a grain size analysis or something like that. So you can say the texture, and then from the texture, you can look in a table and say, okay, loams have a hydraulic conductivity of about 10 to the negative 2 meters per day. So this is something we can look up, and you could do a sensitivity analysis as well on this, plus or minus a factor or an order of magnitude or something like that. So if we assume K, then we can do the rest of this Darcy's law equation. And we're going to use that unit form, right? So we took area out, we took the big Q out. So we've got discharge per unit area is equal to K times dH over dL. And that's going to be equal to 10 to the negative 2 times 0.0064. And remember, K has units of length per time, and our Q also has units of length per time, or little q. And so that gives us an answer of 6.4 times 10 to the negative 4 meters per day for our flow rate. Again, we had to assume a hydraulic conductivity, and we could look at, for example, if we said that this was more sandy loam and it had a hydraulic conductivity of 10, so we'll say K sand is equal to 10 meters per day, then we would have gotten a much different answer, 6.4 times 10 to the negative 2 meters per day. So you kind of look at the sensitivity of this calculation to the hydraulic conductivity. Any questions about that?
So is that how much the water level?
This
Or
is
what's that?
this is the flow rate. So you can
Okay.
imagine that if we have a unit area like 1 by 1 meter in this aquifer, it's moving at a flow rate of, in this case, per unit area, this is 1 meter squared, right? In this case, it would be moving by 6.4 times 10 to the negative 4 cubic meters per day. So that would be the big Q, would be moving through this 1 by 1 area. If you define an area, if you don't define an area, you can just say it's moving, little q is moving at 6.4 times 10 to the negative 4 meters per day. So you could think of that as a velocity, basically.
Okay.
And then under these conditions, under this hydraulic gradient, say you had like a river or something like that over here, then and you know the area of this bank, right, over a distance, length, and height, then you could calculate a flow rate coming into the river, contributing to base flow from this side of the aquifer. All right, so let's do the cone of depression problems. That'll be the last thing we do together. And so we'll just say steady. So our cone of depression problems, and you'll remember that, I'll just draw this up for you. Got an aquifer, got a well, two wells. 1, 2, ground surface, and you're pumping water out of a well. Sometimes you're giving Q, or sometimes you want to calculate Q. And because it's steady state, that's been pumping for a long time, and it's drawn the water down to a certain level that you can measure in the well as well as at an adjacent well. And so there's some terms that we need to know, or some constants that we need to know. We want the radius of the well itself. That's important. You want the radius, and this is from the center line to center line at this other well. We'll just call that R. I'll make that green. You want the H at a well, and you want the H at some other well, so we'll just call that H. Yeah, those are the main terms. And this could also be, you could do this calculation about 2 wells that are near this well. And so if you don't have that information from the well that's being pumped, or you could also do it for another well right here and just have R1, which would be the distance from this well, and R2. So the applications here, there's really just 2 kinds of problems. The first problem is given Q, or sorry, giving Q, actually there's a few more than 2. Let's try this. So giving Q and H, which would be the drawdown at different locations. We'll just say H1 and H2. We could find K. So under steady state conditions, we can find the hydraulic conductivity of the aquifer. We could say given Q and K, find the drawdown, find H at some point, either in the well or nearby. And then also you could say given K and H, find Q. So this could be kind of like a rate limiting thing. So I know my K, maybe I did a slug test or a pump test and I found K. I say I don't want to draw down more than 1 foot at my neighbor's well, which is 1,000 feet away. How much can I actually pump out? So that would be why you do this problem. Or you could say I want to pump out 1,000 gallons per minute. Here's the hydraulic conductivity of my aquifer. How much is it going to draw down my neighbor's well? Does that make sense? All right, so let's do an example problem together. All right, so we have a well that is discharging 75 gallons per minute from an unconfined aquifer. The original water table elevation, so we'll just call that H naught. This would be H naught, really far away where there's not any influence. H naught is equal to 35 feet above mean sea level. After a long time, so under steady state conditions, the water table settles to, we'll just say H is equal to 25 feet above mean sea level at a well that is 75 feet away. And we also have, so we'll call that H1, and then we'll have H2. So this is going to be 2 wells here. H2, we have 34 feet of a mean sea level at 2,000 feet away. All right, so we have a flow rate. We have our different heights. And we are wanting to calculate the K value in this case. All right, so let's just draw that together. So that's our pumping well. Here's our nearby well, and then really far away, we get another well. So we got our little cone of depression. Originally, we were at 35 feet. Here we're at 34 feet. Here we're at 25 feet. And then we'll use our equation. Remember, there was 2 equations for these problems. One was for a confined aquifer, one was for unconfined. And so for the unconfined aquifer, the equation that we're going to use is Q is equal to 2 pi oh, sorry, it's not 2 pi, it's just pi. Pi times K H2 squared minus H1 squared all over ln of R2 over R1. And R was the radial distance between the wells, right? And so R1 is equal to 75 feet. And then R2 is equal to 2,000 feet. What would R1 be if I only had 2 wells in this problem, the well that we're pumping from and another well nearby? What would my R1 be?
The radius of your well.
Correct. So you can do this problem with just 2 wells where you have the drawdown level inside the well itself. And the radius you're going to use is the radius of the well. So if it's a 6-inch well, then your radius is 3 inches. 6-inch diameter well, then your radius is 3 inches. In this case, we're doing 2 different wells far away. Maybe it's hard to actually measure the water elevation in the well you're pumping, right? And so our R1 in this case is the distance, and our R2 are the 2 distances away. So all we need to do here is rearrange this equation and solve for K. So K is equal to Q ln of R2 over R1. That's natural log divided by pi H2 squared minus H1 squared. So I'll have you guys go ahead and calculate this and tell me when you have an answer. One thing to note is that I gave you a flow rate in gallons per minute. And off the top of my head, how many gallons per minute are in a cubic foot per second? Is it 484? No. Yeah, 448. There we go. So I'll note that there are 448.83 gallons per minute per 1 cubic foot per second. For whatever reason, we estimate flow rates out of wells in gallons per minute. All right, anyone got the answer?
I got 25.2 feet per day.
Of course, I calculated mine in feet per second. So let me just 25.2 per day.
Oh, I used the wrong conversion factor for seconds. Sorry.
Okay. Let me just anyone get an answer? And I think feet per day is probably the way to do it. Let me see. I did 2.32 times 10 to the negative 4. Let's see if we can do that.
I'm getting a pretty small answer, which I think is wrong.
What'd you got?
I got 3.8 times 10 to the negative
Times 10 to the negative what?
fifth.
Let me get my good calculator. My phone's not going to do it for me.
What did you say you got, Edgar? 3.2 times 10 to the negative fifth?
3.8 times 10 to the negative fifth.
Okay. I got 3.3 times 10 to the negative fourth.
Yeah, I
So,
got negative 4. And but that was feet per second. Was that what units you guys are doing?
yeah, that's what my 3.28 times 10 to the negative fourth cubic feet per second.
Okay. All right, so let's just over at 75 gallons per minute times 1 CFS over 448.8 gallons per minute times the natural log of 2000 over 75. And then that's going to be divided by pi times all right, yeah, I got 3.3. For some reason yeah, so 3.3 times 10 to the negative 4 feet per second is equal to 28.5 feet per day. Does that look right to you guys?
Yep.
All right. Well, I gotta go. So that's groundwater in a nutshell. I'll post the groundwater homework assignment tonight, and we will, that'll be the last homework assignment. Also post a video for the last project, just to gonna go over it with you guys. And I'll see you on Thursday. We'll talk about some urban water design stuff. Okay.
Sounds good.
All right. Bye.
Bye.